So today I will talk a little bit about the nonlinear photonics, which is an area we are developing in our group in the Institute of Physics of São Carlos. So basically, in our group, in our group, which is called Photonics Group in the Institute of Physics, we are working in several areas, such as nonlinear photonics, photonic materials, ultrafast optics, micro and nano photonics, polymer photonics, and biophotonics. So in this talk, I will mainly talk about those last three topics, which are basically related to the use of femtosecond laser pulses and nonlinear optical interactions to induce changes in the materials to create microphotonic devices, polymeric photonics, and also some micro devices that can be used for biophotonics, which will be the last topic over there. So every time I think about femtosecond laser pulses, it reminds me to my youth when I was a big fan. I'm still a big fan of Star Trek, and then I recall here the Enterprise firing some quantum torpedoes in a Borg cube in the other side. So if you look here at the size, so if you of course, if you go to Google, you can actually get the numbers for the size of the USS Enterprise. And here, of course, then we can use the Enterprise as a type of scale bar for this picture here. And then we can actually estimate the size here of this pulse, of this laser pulse that the Enterprise is firing. So you see that this laser pulse is about 15 meters long. Of course, as we know the velocity of light, we can calculate the time of the pulse that the Enterprise is firing. So it's actually 50 nanoseconds. So as you guys might be aware, so that's like Enterprise is like way in the future. So basically in the future, they are using like not very high technology because they are using 50 nanosecond pulses. So it's actually not a very short laser pulse. But of course, if the idea here is using this laser pulse to cause damage in the Borg or in the enemy on the other side, of course, it's always a good option to use as longer pulses as you wish. But you might imagine that maybe they were using like some sort of very, very short pulses, and that's not the case. So the technique that we use to actually create femtosecond laser pulses or to create ultra-short laser pulses is the one that we call mode locking. So basically here what we do is we have here all, I'm sorry guys, all the modes in a cavity. So if they are not phase correlated, you get a continuous wave laser. So the intensity versus time of the combination of all the modes you have in the cavity, which are not correlated in phase in any ways, is basically a CW or a continuous wave laser. But if somehow we are able to lock the phases, the relative phases of the longitudinal modes of the cavity, you do have some kind of interference between the modes in the cavity, and that creates the femtosecond pulses or the ultra-short pulses. So as you can see here, as larger the number of pulses you get, as shorter will be the ultra-short laser pulses, because you have here in the interference, you have a higher number of modes which are interfering. So of course, that's so there is here a relationship between the pulse duration and the spectrum of the laser pulse, which is actually basically the Fourier transform or uncertainty principle. So basically, if you have a pulse which is long in time, it means that it's very narrow in frequency, in the frequency domain. And then, of course, in order to get a very short pulse in time, you have to have a pulse which is broader in the frequency domain. So I don't know how many of you guys have seen a femtosecond laser before, but that's a titanium sapphire laser crystal. So here is the titanium sapphire crystal being excited by another laser with the green light here. So as you can see, it's a kind of reddish color. And if you look at the spectrum that's being emitted by the titanium sapphire crystal, which actually is the active medium for the femtosecond laser, it's very broad. It goes from 600 nanometers all the way to 1000 nanometer. And and the reason for that is, since we have such a broad spectral emission spectrum, then we can get a very short femtosecond pulse, as I mentioned before. So depending, of course, on the configuration of the laser, you can get pulse duration all the way from 20 to 100 femtoseconds. So how short is a femtosecond? So the idea, so just one step back. So the idea here is having an active medium that presents a very broad emission spectrum, such that we can do the mode locking, so we can lock in phase all the modes of our lasers. Such in this case, of course, we'll get a very short laser pulse. Okay, and how short? So nowadays we can kind of easily get femtosecond laser pulse. So 1 femtosecond is 10 to the minus 15 of a second. So we like to use this picture here just to give an idea of how short is a femtosecond. So here 1 minute is 10 to the 1 of a second, 1 month is 10 to the 6th of a second. Here the age of the universe is 10 to the 16th of seconds. The camera flash is on the order of 10 to the minus 4 of a second. The Pentium clock, or the clock of a computer, is 10 to the minus 9 nanoseconds, and 10 femtoseconds is 10 to the minus 14. So basically, 1 minute is to the age of the universe. In the same way, 1 minute is to 10 femtoseconds. So that's how short is a femtosecond pulse. Another illustration that I like to use to express how short is a femtosecond is this one here. So in this picture, I'm showing the electric field of a femtosecond laser pulse at 800 nanometers, so in the near infrared. So as you can see, this pulse here, it goes from minus 10 to 10, so it's about 20 femtoseconds in duration. At 800 nanometers, it means that the electric field has only time to oscillate 1, 2, 3, 4, maybe 7 times. So when we are talking about electromagnetic waves in this femtosecond domain, it means that the femtosecond lasers is not a wave that oscillates a lot. It doesn't have time to the wave oscillate several times. So as you can see here, for these 20 femtosecond pulses, the electromagnetic wave only oscillates a few times. So in the middle 80s, after people have already created femtosecond laser pulses, so of course you have a very short laser pulse, then you can get very high energy. But then in the middle 80s, these two guys here, Professor Chehamo Hu and Professor Don Strickland, they proposed a method which is called chirped pulse amplification. It's CPA, which actually is the way we can amplify femtosecond laser pulses. So of course, a femtosecond laser pulse has already very high intensity, and then you can do lots of physics with such very high intensity lasers. But of course, if you get higher intensities, you can get even nicer physics. So basically, so in the middle 80s, they invented this method, which is called chirped pulse amplification, and they won the Nobel Prize in 2018, so a few years ago. So what's a chirped pulse? So I don't know how many of you guys are familiar. I'm pretty sure some of you are familiar with that. I'm just trying to read some names. Okay, Vinicius for sure is very, very familiar with this. Anyways, so here, what's a chirped pulse? So a chirped pulse is a pulse in which the frequency of the pulse, it changes with the time. And the word chirp is from the chirp of the birds, right? Or in Portuguese, o pio, or o gorjeio of the birds, of the pássaros, right? So basically, what I'm saying here is the idea is, as you can see in this picture, the frequencies are not homogeneously distributed in time. So the frequencies, the lower frequencies are here on this side of the pulse for shorter times, while higher frequencies are on the tail of the pulse, right? So that's what we call chirped pulse. So it's a chirp in which you spread in time the frequency components, right? And we use actually the same word in Portuguese. So what's the idea behind using chirped pulse amplification in order to get this amplification? The idea here is the following. So they have this femtosecond pulse, which is not chirped. You see, So all the frequencies are homogeneous distributed. And then they send it to these gratings. And then by doing the grating, you chirp the pulse. So when you chirp the pulse, the red components go ahead while the blue component stays behind, right? Because of dispersion. And then the pulse, which was very short in time, it becomes longer in time. And then you do the amplification, right? Because if you try to amplify such a short pulse, the intensity that you have will be so high that you damage all the samples, all the materials, all the glasses, and you damage everything. So that's the idea that they had. Of course, it's a very simple cartoon just to illustrate what's going on. But basically, you chirp the pulse, so you spread the pulse in time, then you amplify, and then afterwards, you recompress the pulse, with a much higher energy. So by using this, by developing this method here, they allow several new technologies using femtosecond laser pulses. So just to illustrate, I'm gonna show some pictures of two labs. Here, that's a femtosecond laser pulse, which has a CPA amplification, operating at 800 nanometer. That's another laser also. So this laser here delivers 150 femtosecond pulses. And this one here delivers 40 femtosecond pulses. That's also a laser which has a CPA inside. So, okay, so nowadays in our labs, we can get femtosecond laser pulses all the way from 100 to 20 femtoseconds. And of course, because we have such energy in a very small time interval, we can get very high intensity if we focus such power in a very confined space, right? So with that, we can get intensities now, for instance, we can get intensities as high as 100 gigawatts per centimeter squares using femtosecond lasers. And that's actually very easy, right? I'm using that, I'm not even like getting closer to the maximum I can get with our lasers in the lab. But anyways, so as a comparison, so maybe many of you guys are very familiar with laser pointers, right? If you get the intensity of the laser pointer, which is actually the power divided by the area, right? So that's the intensity, which is actually power density. That's something on the order of 10 to the minus 3 watts per centimeter squares. So as you see here, there's a factor of 10 to 14 in intensity. So that's okay. That may be not a super fair comparison, but that's a comparison for a colloquium, right? So you get an idea of what's going on. Anyway, so what happens when we get such very intense laser light? We induce what we call nonlinear optical phenomena, right? And what's a nonlinear optical phenomena? Nonlinear optics is something that happens between in the light matter interaction when we get very intense light, laser light. And actually, as I'm going to show in the next few slides, and not really only any laser light, but we need mostly femtosecond laser lights. And what changes then? It changes that in the constitutive relationship, the polarization induced in the material when we are in the nonlinear optics domain, the susceptibility is not a constant anymore. It depends on the electric field, right? And in this case, the optical properties will also depend on the intensity of the light. So absorption, refraction, for instance, will depend on the intensity. So how high should be the intensity, the light intensity, for us to observe nonlinear optics? So we have electric field, and here we have our electron in our atom. So we have nonlinear optics every time the radiation, right? The radiation electric field is on the order of the interatomic electric field, right? So just in order to estimate the interatomic electric field, let's get here a Bohr atom, and let's take here a radius of this this Bohr atom of 4 angstroms, and then you get this electric field on the order of 10 to the 8 volts per centimeter. Okay, just like a very simple calculation. Okay, so that's the order of magnitude of the electric field that we get. My kids are yelling downstairs. I'm sorry, guys. They are like playing some video game or some craziness down there, you know. Anyways, there we go. And then, okay, that's the order of magnitude of the electric field. For a CW lasers, for a continuous wave laser, I'm representing here, I'm focusing, let's suppose that I'm focusing the laser in this spot here, and the spot is 20 microns in radius, right? So 20 microns is like, what, maybe 1/10 of the hair, right? And then I'm focusing 20 watts. 20 watts is a very powerful continuous wave laser. So that's the kind of laser that you can use to, you know, to cut metal, for instance. Then if you calculate here the intensity, you get something on the order of 10 to the 10 watts per meter squared. And then you use the Poynting theorem. And then you get, right, by, you plug here the intensity, and then you calculate the electric field of your laser. And then you get something which is 10 to the 4th volts per centimeter, okay? So as you can see, even if I focus this laser here, which is 20 watts, that, you know, can be used to cut metal very tightly, still you don't have enough intensity to get to the interatomic electric field. But of course, when you use now pulsed lasers, in which you can get intensities on the order of hundreds of gigawatts, and then you get now the electric field on the order of 10 to the 7th volts per centimeter, okay? So as you see here, now we are approaching the same order. Of course, if it's a molecule in which the electron is farther from the nucleus, then you have a smaller electric field, and then this guy here is going to decrease, and this guy here depends, of course, of the intensity of the laser. But as you can see here, with femtosecond laser pulses or with pulsed laser, you can get the electric field, the radiation electric field, on the same order of the interatomic electric field. So in order to get actually a nonlinear light-matter interaction, we should be in this regime. So from the theoretical point of view, we can use perturbation theory all the time we are in this perturbative regime, in which the electric field is on the order of the interatomic electric field. But of course, if now the electric field of the laser is higher than the interatomic electric field, we are in the regime that we call the extreme nonlinear optics, in which the perturbation theory does not apply anymore. Okay, guys, so what happens then when we are in this intensity there, right? So is in the high intensity, we have nonlinear optics, and then what happens is that the polarization induced in the medium is not only this term, which is the one that we learn in the undergrad courses for electromagnetism. Now we have what we call the second order nonlinearity, which goes with the electric field square, plus the third order nonlinearity, which goes with the electric field cube, so on and so forth. So we have higher order polarization induced in the material. In each one of these higher order nonlinearities give rise to different nonlinear optical processes. So how so? So basically here you have the nonlinear wave equation, but now the polarization here on the right hand side of the nonlinear wave equation, it has this nonlinear polarization. So now the matter-light interaction is actually driven by a polarization which is nonlinear, right? So, and because of that, we can get several different processes. So just to give you an idea, for second harmonic generation, for the second order process, you can get second harmonic generation. So I'm gonna explain this quickly just as an illustration. So basically here you have a microscope objective, a lens, focusing the laser in this tweezer, which a nonlinear crystal. So here it's an infrared laser, that's why we can see it at 1200 nanometers, and then when it gets to the sample, you generate 600 nanometers. Here, the laser operates at 1000 nanometers, and then of course, you generate second harmonic. So you double the frequency, meaning that you decrease the wavelength by half. And then you get the green light, and here you use 900, and then you get 450, which is blue light. So basically, it's a crystal which is actually completely transparent, and with that, just because the nonlinear interaction is so high, you get this term, which goes with the electric field square, and then you get second harmonic generation. That's another second harmonic, and that's a higher order processes in which you shine a piece of glass, transparent glass, with a femtosecond laser, and you can get on the other side a white light continuum generation. So if you go for third order nonlinear optical processes, to Chi3 as we call, so that will be a complex quantity, and then you have the real part is the one which is responsible for what we call the nonlinear index or refraction, or for the nonlinear absorption here. So of course I'm not going into details here, but every time you have a material which presents a Chi3 nonlinearity, you can get a total refraction which depends on the intensity of the light, as you see here. And N2 is called the nonlinear index of refraction. So now, let's suppose, for instance, that N2 is positive. So as higher the intensity, higher will be the refraction of the laser beam. The same applies for the absorption. So we have here what we call the nonlinear absorption, and beta here is the two-photon absorption coefficient. And of course, we can have multiple photon absorption, such as 3, 4, 5 photon absorption, but in this case here, when it goes with the intensity only, is what we call the two-photon absorption. So again, a material has a given absorption, but when you actually shine the material with higher intensity, you get higher absorption, higher total absorption. And that's something that only happens when you have higher intensities, when you are in the nonlinear optics domain. So such process of two-photon absorption was theoretically described by Maria Guppert-Meyer, who actually won a Nobel Prize in physics in the 50s. And then basically, on the theoretical point of view, the explanation is that the intensity, because the intensity of a femtosecond laser is so high, so the flux of photons is so high that it may be possible that two photons are simultaneously absorbed in the same quantum act, promoting the system, the atom from the ground state to the excited state, right? So that's what we call two-photon absorption. Of course, if you extend, so here we use basically perturbation theory, and then you can calculate, for instance, the transition rate for two-photon absorption, three photons absorption, and four photon absorption, right? And of course, it's not easy to observe 3, 4, 5, 6, 7 photons absorption, but nowadays with femtosecond lasers, and depending on the materials, that's something that you can get in the labs. Okay, that's basically a little bit of background. So, in our lab, as I mentioned before, we work in nonlinear spectroscopy. We try to study and develop materials for materials that present higher nonlinearities. That's one part of the lab. In the other part of the lab, we actually use the light-matter interaction to do what we call the fabrication of photonic devices. So the idea here is to fabricate two-dimensional structures or any kind of structures using femtosecond lasers and using this nonlinear light-matter interaction to actually get materials that can be used for photonic devices. So as I mentioned before, when we use femtosecond lasers to do this fabrication, this microfabrication, as I'm calling here, the photon energy is smaller than the band gap. Then the only way I will have an interaction here would be by some kind of nonlinear interaction. So the idea is, here's the band gap, and here's the energy of the photon. So as we know, there is no way that this photon will promote a transition from here to the excited state because I don't have enough energy coming from the photon. But of course, as I mentioned before, if the intensity is very, very high, I might have multi-photon absorption. So in this diagram here, 4-photon absorption, which will actually promote an electron from the ground state to the excited state via this nonlinear interaction. what's good about this kind of nonlinear interaction is that it gives us a spatial confinement of the excitation. So if I have a lens, I'm focusing the lens here in a given material only around the focal volume, the intensity will be high enough to promote such multi-photon absorption. So this picture here illustrates it very well. So there's a cuvette with a given dye which exhibits fluorescence. So that's a laser operating the one photon absorption, so linear absorption, not in nonlinear. So as you can see, as the laser passes through the sample, you see the luminescence of the material, right, everywhere, because it's one photon absorption. By here, this laser is focusing here in this point. So as you can see, only in the focal point, the intensity will be high enough to induce the multi-photon absorption and then excite the molecule, which will then present its emission. So as you see, the laser beam, of course, is passing from here to there, but the intensity is not high enough. Only on the focal point, the intensity is high enough. So you see the localization of the excitation, and that's something that we use for microfabrication. So what we can do with that? So we can focus the laser beam inside a given material, and by controlling the nonlinear interaction, we can modify that material to produce three-dimensional optical circuits, for instance, right? So as I'm showing here, we can fabricate kind of waveguides, which are, let's call like optical fibers, which are actually immersed inside or in the bulk of a given material. So we can, by controlling the movement here, of course, by controlling the intensity and the number of pulses and like lots of things, we can actually fabricate waveguides. Here I'm going to show a result of the waveguide fabrication in Gorilla Glass, just for illustration. So Gorilla Glass is the one that we use, that we have as the protective layer in our smartphones, and of course it's already integrated with electronics. So of course it would be very interesting if we can integrate also photonics in our smartphones. So the idea is, can we fabricate waveguides, so ways to guide light in such Gorilla Glass? And of course the answer is yes, but for that you have to use femtosecond lasers, because Gorilla Glass is very tough, as we know. And then the only way you can fabricate in Gorilla Glass is using femtosecond laser pulse. So here I'm showing some pictures of guides fabricated in Gorilla Glass. So here is another picture of a 15 millimeters long waveguide. So that's a top view, that's a microscope image, top view of the waveguide. So this waveguide here is not on the surface. It's 100 micrometers below the surface. So it's there in the middle of the sample, more or less. And then if I now take this sample and couple lights, here I come with a helium-neonium laser. That's very standard laser. I focus that on the on the sample, and then you can get light being guided. So here's the transversal view of the waveguide. So you see the waveguide, and then when you couple the light, you see the light being guided in our guide fabricated on Gorilla Glass. Here's some other pictures. So here's the waveguide again, and then of course we can actually see the modes of waveguides, of light being guided at different wavelengths. Because it's a tough glass, we can also do something nicer, which is, instead of just coupling a very weak laser, we can couple a femtosecond laser in this Gorilla Glass waveguide, and then in this case we can get an effect which is similar to the white light continuum generation that I mentioned before. So here the gray line is the spectrum of the laser I'm injecting in my Gorilla Glass waveguide. And then when I increase the power, I generate much more spectrum by a process which is called self-phase modulation, which is also a nonlinear process related to Chi-3 nonlinearities. Then if I now increase even more the intensity of my laser that's coupled to the waveguide, you see that you can generate white light in the waveguide. So you can actually generate and guide the white light. So here is the output of the waveguide, the transversal view. And as you can see, at the beginning, the light was here at 775 nanometers, which is kind of red, right? It's the infrared, but we still can see it. But then, because of this nonlinear process in the waveguide, so it's a nonlinear waveguide, we can actually generate white light in the waveguide. So one question we always get when we fabricate those waveguides using femtosecond lasers is that, but when you do it, don't you, so let's suppose that I have a glass which is very nonlinear. So it's a glass that presents very nice nonlinearity, so I can use that for a given application. Okay, so when I do the fabrication, do I degrade the nonlinearity of the waveguide? So in order to study that, we actually perform this experiment here. I'm not gonna go into details, but basically I have a stretcher of the pulse here. So I take my 50 femtosecond laser pulse, I send it to this part of the setup, and then by controlling the setup here, I can actually control the duration of the pulse. And then I couple that light now in which I can control the pulse duration in the waveguide, and then I analyze the output of the waveguide, and I analyze how much nonlinearity I'm getting here from my my fabricated waveguide as a function of the dispersion of the pulse. And then what we can get is something like this, which is actually how broad is the pulse. So how many new frequencies I'm generating here in the output of the waveguide as a function of the dispersion here in the dispersive line. So that's what I'm showing here. Here is the dispersion, and here is the broadening of my femtosecond pulse. Okay, so what we can get from here? We can get, and of course this broadening is related to the nonlinearity N2. So as we can see here, so what we learned is that for waveguides fabricated with 250 nanojoules, the nonlinearity is 3 times smaller than the one for the glass itself. But of course, when you fabricate the waveguide with much higher energy per pulse, you get a nonlinearity much smaller. So indeed, we are decreasing the nonlinearity by femtosecond laser microfabrication, but we still have some nonlinearities and maybe controlling the energy used in the fabrication. You can get a nonlinearity which is usable for applications. Another thing we are doing in our lab is using femtosecond lasers in order to produce NV centers in diamond. And of course, the idea here is people have been using in the last few years NV centers in diamond as solid state qubits for quantum information. That's very interesting, but of course, in order to have a device, you would have a device for quantum information. You have to have your NV centers localized in a given position in space, right? And then maybe one tool to do that is using femtosecond lasers in those NV centers. So basically, a NV center here, which stands for a nitrogen vacancy center. So it's basically a defect in diamond in which here the nitrogen, as you can see by this blue sphere here, it replaces the carbon atom and it is adjacent to a vacancy. So that's this defect that's called the NV center. And the good thing about that for quantum information is that the state energy of this defect here can you can optically initialize the defect center. It has a long coherence time. You can create protocols to manipulate the spin. So it's very interesting for quantum information people. So what we did, so we actually tried to generate those NV centers in given positions inside diamond. So here are the positions where we radiate with femtosecond lasers with different illumination times. And then in the end of the day, what we got is this luminescence. So the diamond, so when we excite at 532, which is green light, the diamond doesn't fluoresce. But if you have the NV center presents some fluorescence. Those pictures here are actually the fluorescence of the NV center. And of course, we can actually measure the fluorescence spectrum just to confirm that we do have the NV center, and that's exactly the signature of the NV center with this peak at 637 nanometers. So using femtosecond lasers, we are able to actually fabricate in localized positions in diamond, for instance, the NV centers. And then, of course, there's a good option for quantum technology. Another technique that we actually use to do this fabrication of micro and nano devices is the laser-induced forward transfer. So basically, here is something a little bit different. So we have a substrate here. I have another substrate, let's say a glass substrate, and then I have a donor material. So basically, I focus the laser beam here in the donor material, and then I actually explode or I melt this material in such a way, that I can actually fabricate, I can transfer material for this donor substrate to the receiver substrate by using femtosecond lasers in a very controllable fashion. So here, what I'm showing are some spheres. So as you can see, these spheres, they have about 2 microns. They are very, very regular, and they are made from silk fibrin. So silk fibrin is the protein, and silk fibrin is silk fibrin. So silk fibrin is the protein from silk, right? Which is a biopolymer that's being used for several applications in photonics and in biophotonics. Right. So in this case, we are actually transferring this biopolymer using a laser-induced forward transfer lift, and actually those spheres here, they contain rare earth, so they contain erbium and terbium, so they are actually luminescent. So you can actually get some structures which are actually somehow like cavities emitting light in the green or in the red, depending on if it's doped with europium or if it's doped with terbium. So that's something we are able to do. Something else we are doing is fabricating photonic crystal structures. So in this case, by using lift in chalcogenide glass, arsenical trisulfide, we are able to fabricate those structures. So as you can see here, every part here of the structure has about 150 nanometers, and the idea here is to create a quasi-periodic structure that can act as photonic crystals. We are doing some modeling, and now we are trying, so we did some modeling for the photonic crystal, for the gap of this material, the photonic gap of the material, and now we are trying to analyze or try to get the results. So we actually model, we fabricate, and now we are trying to measure the band gap, the photonic band gap of the material. So the last part of the talk, so I'm getting towards the end, is another technique which is called femtosecond laser, which is called two-photon polymerization by femtosecond lasers. So in this case here, the idea is fabricate those three-dimensional microstructures using polymeric materials in such a way that we can get active or functional elements, because polymers is kind of easier to incorporate materials that can be used for different purposes, right? So what's the concept here? So we have a monomer, which is a kind of a viscous liquid. We add a photoinitiator, which is a small molecule, which will be excited by our femtosecond laser light. We will be excited by two-photon absorption. And this photoinitiator plus the monomer here, we will start the polymerization reaction. So in the end of the day, I go for this, from this viscous liquid to a solid piece of plastic, right? Which will be induced by two-photon absorption. Again, because it's a two-photon absorption, I'm focusing my laser here in the focal spot. So only around the focal spot, I have enough intensity to induce the two-photon absorption and then to excite the photoinitiator to do the polymerization reaction. So I have a very high spatial resolution. Here is the setup. So basically my laser beam, some polarizers, and doesn't matter much. But anyways, I have here a pair of mirrors to move the beam in X and Y direction. And then it passes here and go to this microscope objective with focus here on my sample, which I move in the Z direction. So I have control of X, Y, and Z, and then I can fabricate any kind of three-dimensional structures. So here is a movie just for illustration. The laser beam is scanning here. So the material is being polymerized. It changes the index of refraction. That's why you see this picture going on. So here is a fabrication of 2 layers. It's 30 microns by 30 microns by 12 microns tall, right? So that's a real-time movie. Of course, we like to say that in Rio de Janeiro, they have the tallest Christ of Brazil, but in São Carlos, we have the smallest one, right? So here is a Christ we fabricate in our lab, which is about 20 microns tall, right? So that's a scanning electron microscopy image of the Christ. So we have a feeling. So this Christ here, the height of the Christ, it's maybe 1/10 of the hair. But of course, that's just to illustrate that we can fabricate any kind of complex structure. So depending now on the purpose you have in mind. We are working on fabricating microresonators, polymeric microresonators. And the idea here is to have this kind of resonance structure made out of polymers that in order to confine the light here by total internal reflection. The idea is we have this very tight confinement. At the same time, we have like a high quality factor, a high Q. Is very sensitive and is also, you can select the frequency. And we use polymers for that because, okay, it's low cost, but I mean, that's not the main thing here. But the main thing is polymers is easy to functionalize. So I can fabricate a resonator in which I can incorporate other materials for a given application. I'm going to show you something right in a little bit. So here, a better picture of our resonator. Of course, since in this case we're fabricating a resonator, we have to have the roughness of the surface to be very, very small. Otherwise, we will scatter the light that I'm trying to couple to my resonator. Here is an atomic force microscopy of our resonator. As you can see, the roughness, the average roughness is on the order of 1.9 nanometers. So it's very good. It's a very nice resonator that we are able to fabricate. And then we couple light to the resonator. How do we couple light in the resonator? We get an optical fiber. We hit the optical fiber and we pull it. We're creating this kind of shape here that we call a tapered fiber. We couple light here in this optical fiber, and then some part of the light leaks, right, by the evanescent field, and then couple in the microresonator, and then I see the light that passes through. So I can measure a transmission spectrum of my resonator in this way. Here is an actual picture. As you see here, the resonator and the optical fiber on the back, and here is the resonance spectrum of the microresonator. So as you can see, we have like different resonance that we can get depending on the modes we are getting there. The free spectral range is actually the one we are expecting, so everything works fine here. The quality factor, so by getting one of these resonances, we can analyze it, and then we can actually estimate the quality factor, which is 10 to the 5th, which is actually the limit for such kind of resonators, polymeric resonators. So there is not much way to increase the quality factor. So, but it's actually a very competitive quality factor. But then we dope, so we incorporate in our resonators rhodamine B, which is a very fluorescent probe, a fluorescent dye that's used for laser emission. So rhodamine B can be used for having laser action. And then so now I have my resonator containing rhodamine B. I excite the resonator with the green light. So the green light will be absorbed by the rhodamine B, and then I have the emission of rhodamine B, and then I have an optical fiber coupled to my resonator to see what's going on. So here's the optical fiber, here's the resonator. As you can see, the resonator now is red. That's the emission. Because of the rhodamine, the rhodamine that is incorporated in the microresonator, and then now I collect the emitted light, and then I can see now the emitted modes of my laser cavity. So I do have a laser cavity here. If now, so that's for the, each curve here corresponds to a given excitation power. So now I can plot here the intensity for, as a function of the emission intensity as a function of the emission intensity as a function of the excitation intensity, and then you get here the profile of the laser. So here is the threshold of the laser. So we can get laser action with very small excitation energies. We have also been able to incorporate graphene oxide in those microresonators, and the idea here, of course, was to evaluate the nonlinearities of graphene in these microresonators. So again, a microresonator, we incorporate graphene. So we see here that will be the pure resonator, and then when we have graphene, we have like a higher Raman spectrum, just to actually prove that we do have the graphene in our resonators. And then what we see is the following. So for the pure resonator, the resonator without the graphene, that's the spectrum we get. And for the resonator with graphene oxide, GO, you have much fewer lines, right, resonances. That means that we do have, like, and you see here that the Q factor is not that much different. So the Q factor, right, is about the same. The quality factor of the resonance is about the same, but the number of modes diminishes a lot when I incorporate graphene, and that's what we're calling a mode cleanup. So we are cleaning the modes by using graphene. So we have like much fewer modes in our resonator. We actually did some simulation in which, so here's the pure resonator, here's the simulation, using the pure resonation and incorporating in our modeling here the losses in the resonator induced by the graphene oxide. We get this curve in which we can actually see that just because of the losses of the graphene, we have a smaller number of resonances, which kind of resembles the experimental results. Okay, the last topic then is using such three-dimensional microstructures fabricated by two-photon absorptions to biological applications. So here, one thing that we are working on right now is using two-photon polymerization. So that's a microenvironment. So it's not only a given cylinder, but it's like a set of cylinders which are basically on the size, which is interesting for studying the cell growth. And which kind of cells? So this one here, I'm not gonna pronounce this thing, right? This guy, so this cell, which is this cell here, right? This bacteria, I'm saying cell, it's not cell, it's bacteria. So this bacteria here, right? Which is a bacteria which produces bacterial cellulose. So it produces cellulose, BC. So as you see here, those purple structures are actually the bacteria, and the other parts around is actually the bacterial cellulose. So bacterial cellulose, it's a biopolymer. It's completely biocompatible. It's being used for tissue engineering, for drug delivery. So basically, if you have a bunch of this bacteria in a bath, like a big bath, in the end of the day, you get this kind of membranes. So this, which color is this? This color here, it turns in a membrane like this one here. So you can actually get a cellulose membrane, which is actually not from the tree, but from the bacterium, from the bacteria. So that's why people call bacterial cellulose. So it's the cellulose which is actually produced by the bacteria. And the idea here is actually to use those microenvironments to guide the production of bacterial cellulose. So as you can see here, we have this microenvironment. We incubate the bacteria here, and after 24 hours, as you can see here, we have this film covering everything. So, and then of course we can use those microenvironments to understand how the growth and how the movement of the bacteria develops in order for tissue engineering applications, for instance. We also made this labyrinth, for bacterial cellulose, so this kind of thing here, and then we actually inject the bacteria, so we actually incubate the bacteria in this side. But as you can see, at first we thought that the bacteria would cover everything here, and then we'll have cellulose everywhere, but as you can see, it doesn't happen. I only have bacteria on the smaller parts here, on the smaller distances of my labyrinth. It seems that the bacteria uses the labyrinth as a support for growing and then for producing the bacterial cellulose. So lastly, another thing that we are able to do is we can fabricate those microstructures containing two different dopants. So in this one here, just as an illustration, I fabricate this kind of structure, which is a part of a cone with a cylinder on the top. And each part of the structure contains a different emissive dye. So this one here has fluorescein and rhodamine, right? So that's just to prove the concept. So I can have only a single structure which has two different, of course, there's like lots of strategies to produce it, but we can have a single structure that has different functional materials. So what we did with that, we fabricate this microenvironment in which it's a bunch of cylinders. Here's a scanning electron microscope image. So I have here several cylinders, but only the one in the center has this compound here, which is an antibiotics, right? And then, so now I have a microenvironment which has a given geometry, but also has this kind of dopant, or the antibiotics. And then we can study how the bacteria, in this case here, the E. coli, Escherichia coli, how it develops in this microenvironment, which can be, of course, used for studies in drug deliveries and also for other systems. Okay, guys, so that's more or less what I had to tell to you today. So if you have any questions, or if you want to have a look in our webpage, you don't have to remember anything. You just go to Google and you Google Photonica USP, and we are going to be the first hit there. Of course, everything I show here, I just like pop up some results for you guys, but it's like a collaboration between several people from our group. So we have like a few postdocs, a few students here, and the part on the NV centers and diamonds is a collaboration with Professor Sergio Muniz, also from the Institute of Physics. And of course, I have to acknowledge FAPESP and PQ, CAPS, and US Air Force and US Army for funding our research. And that's it. So I'll be happy to take any questions you might have in English or in Portuguese. So thank you.
Okay. Thank you very much, Cleber. Are there any other questions?
I have a question. Very nice, Cleber. It's very nice to see the overview that you can apply these ultra short pulses in a lot of stuff. But there was one thing that I recently saw, that people are starting to apply these ultra short pulses on Rydberg systems, because like the NV centers, there's also the problem that you have to control coherently these things that decay too fast. And do you know if is there any plan of your group to apply this ultra short pulses in ultra cold atoms? This kind of, you know, it would be another slide for you, because I know that's a bunch of stuff that you're doing, but
no, I mean, not myself, okay. Right? Because that would be too much, right? That would be.
Yeah, I mean, it's a lot already. I was impressed that.
I guess. I mean, not myself, right? I imagine that some people, I guess Marcassa, some time ago, he was like considering some experiments with femtosecond laser pulses in his Rydberg atoms. But I guess he was interested in something else. But you know, Rydberg atoms and quantum information,
yeah,
right?
Yeah.
But I guess at that time he was. I can't remember very well. I guess he was trying to do some impulsive excitation in the potential that he has there in his trap. But no, not specifically like in. Okay, Marcas and I, we belong to the same group, but we are in completely different labs, right? So it's not like there's even, so Marcassa also belongs to the photonics group, but it's like a separated research line. One thing we are trying to do, we are trying to explore silicon vacancies in diamond. That's something, right? Which might be interesting as another option of a color center that can be used for quantum information. And some people think that it might be a better option. And we are also working on silicon carbide right now. So we have some studies. Of course, we had to stop that because of the COVID pandemic, because that was something that we were starting in March. And of course, we have to stop to stop. But that's something else we are like doing more towards, but not really with cold atoms.
I see, but the NV centers. Are you planning to do experiments along these lines of playing with qubits, this kind of stuff?
Not myself. Not myself in my lab.
But you can create the platform, and then people can use it, right?
Exactly.
Because Homa and I actually we recently published a paper that we suggest some things that are very similar to what happens in Rydberg physics, but it could also be straightly applied to NV centers. So it would be nice to know if IFSC is doing this kind of experiment, because we have some ideas.
Cool, but I mean, so so we have this collaboration with Sergio Muniz, right? And he's the one, so he's the one more like towards quantum information. So our idea in our side of the collaboration is basically creating the NV centers in like given position, and then maybe Sergio, he will try to do he will try to perform some quantum information experiments.
Oh, but it's really cool. That's really nice.
Thank you.
Okay, thank you.
Thanks.
Okay. So we have a question in the chat asking whether you use a femtosecond laser to study the crystal structure, like phase transitions, melting.
Yeah, I mean, we actually also have some works in which we use femtosecond lasers to actually study phase transitions. Okay, I guess the word study the transition is maybe too hard for me, but maybe what we do is we do melting, and we do transfer the material by melting sometimes. So we actually study how is the best conditions to do melting, or that's something that melting and then resolidification. That's something we actually study. But not like really trying to understand, the mechanisms or the theoretical mechanisms behind the phase transitions. Let me see here. I'm asking because it would be interesting to compare. We do melting. we try to get the proper conditions for melting sometimes. But I don't know about, like how to get some information on the melting mechanism that we would have in this short time interval that we have the interaction with femtosecond lasers in order to try some theoretical models or some theoretical calculations.
So I have a question about the nonlinearities, the Chi2, Chi3. So you said, in general, you expect that absorption will increase with the laser power, or can it decrease?
That's a good question. So if it's a multi-photon absorption, Roman, it's always increases, right? Because the absorption is always positive. However, there is other mechanisms that people call, so that's what we call in our field pure electronic nonlinearity. So basically, it's a multi-photon absorption. It's a Chi3, Chi5, Chi7 process. So in this case, you always increase, right? However, sometimes what happens is that because the intensity of the laser is so high, you can you can promote transitions from the ground state to the excited state in such a way that you deplete the ground state. And then the population mechanism depends on the intensity. So the population rate of the excited state depends on the intensity. So it's not a chi3 related process, it's a chi1, but then it's a chi1 that depends on the intensity because the population depends on the intensity. And then if the transition from the first excited state to the second excited state has an absorption cross-section which is higher or smaller, then depending on if the transition from the first excited state to the second excited state is higher or smaller, then you can get a decrease or an increase in the nonlinearity. That's also it's also so we call that saturation of absorption or reverse saturation of absorption. That works. We see that a lot, to be honest with you. But it's interesting for like spectroscopy. It's a very cool process to study too. However, it's for application, depending on the application, the dynamics of the process depending on the excited state dynamics. So it's kind of low. It's low process.
Yes.
Right? It's not ultra fast. Sometimes it's only nanoseconds, maybe a few picoseconds.
Okay. I was asking because it's exactly this with if you have two level atoms and you drive on this transition with a lot of power, you will saturate everyone and you will bleach the medium, so the light will cross, so absorption decreases. Exactly. But it's this kind of okay. I understand now why if it's multi-photon, you need to put more power to
exactly
to get some process.